Hello everyone. I'm Chang from OPPO, and I appreciate the opportunity to attend this conference. This is my first English speech, so excuse me if I have any grammar issues or bad accent. I'm the maintainer of open source project CubeFS. And I also in charge of the file system of OPPO. Well, let's get started now. Today my topic is CubeFS in action, empowering users through case studies. My speech will include 3 parts. First, I will introduce the architecture of CubeFS. Second, I will introduce several end-user cases. Finally, let's review the future prospect of CubeFS. CubeFS is a next-generation cloud-native storage system. CubeFS joined the CNCF in 2019. After about 5 years of development, we released around a dozen versions in the past few years. Finally, at the end of the last year, we graduated from CNCF. The picture is from the CNCF website. In terms of the architecture, CubeFS is an independent and self-governing storage system. As can be seen from the diagram, it includes several parts. The part in the top left is the client subsystem. The client is actually a very complex component. It provides capabilities for different interfaces, such as S3, ADFS, and POSIX. Meanwhile, the client side interacts with the backend frequently, and even gets the whole process of our system. The middle part on the left is the cache subsystem. The cache system is a new designed system for adapting to different acceleration scenarios. Currently, to support AI, the cache system is becoming more and more important. This is a main point in my topic. The lower left corner is a metadata subsystem. It's carefully designed. It has strong consistency and can be scaled easily. Many system-level functions like the trash, audit, and atomic POSIX interfaces need support from the metadata subsystem. On the top right is the object access system. Different from the traditional object storage architecture, CubeFS achieves a capability based on the file system engine. And this system can be considered as a centralized proxy system. The system in the bottom right storage subsystem is a data subsystem. The storage subsystem contains 2 engines. One is the multi-replica engine, and another is the initial coding subsystem, which is independent storage subsystem using the initial coding algorithm. It has its own metadata management, including the inspection and management system, persistent layer, and so on. Now, let me highlight the features of CubeFS. Firstly, CubeFS supports multiple protocols. Secondly, CubeFS has 2 storage engines, including multi-replica and initial coding storage engine. Thirdly, all the main components achieved a strong consistency based on Raft and Quorum. Fourthly, the distributed cache capability can be used in the acceleration scenarios. Fifthly, the intelligent data tuning helps to migrate data from the high-performance media to the lower media to help the business to cut the budget. Finally, You can use CubeFS on Kubernetes via the CSI plugin. Next, I will introduce several end-user cases where CubeFS applied. The first use case is building AI storage based on CubeFS. In recent years, artificial intelligence has brought us tremendous changes. In fact, every industrial upgrade brings both challenges and opportunities to storage. From the previous internet era to current AI era, each time it has brought about improvements for storage, such as the architecture, scalability, and the performance. So in the area of AI, what specific challenges are we facing? At OPPO, the file storage team has been supporting AI-related business for over 5 years. The business includes computer vision, large language model, and multimodality, and so on. From the architecture diagram, we can see some of the upstream and the downstream components and services related to AI in Kubernetes environments. The blue parts in the picture are the sections related to the storage. The top layer is the service layer for specific of AI products. The model layer is AI main workflows in the cloud native environment. There are several storage-related parts, such as AI codes and their online editing and sharing capabilities, data integration, AI training workflows, and model storage and distribution. CubeFS has also developed a feature that enables the acceleration of framework. The feature accelerates data reading by prefetching through adapting a storage plugin in PyTorch. The bottom layer is the infrastructure layer. This layer includes storage computing power as well as some network capabilities. Okay, next, let's start the main process of artificial intelligence and explain in detail its requirements to storage. Just as introduced before, artificial intelligence can be divided into 3 stages, including the process of data processing, training, and inference. Data processing actually means that data sources will write data into storage system, and at the same time, a large amount of data filtering, cleaning, and will be carried out. Here, CubeFS has the capability to handle different data sources, reducing the business pressure of moving data from a different storage system. It can also handle a tremendous amount of data storage based on its scalable capability. The second stage is model training. For most training scenario, data reading is a repetitive process. A large language model may be an exception because it can load all the data at one time. But for a training process like the computer vision, data reading needs to be done multiple times with a high probability. Here, CubeFS has a capability to handle high throughput with low latency. The third part is the inference stage. In this stage, the model generated in the second stage be used. For AI platform, it is necessary to distribute the models to the endpoint quickly. The distribution process requires high throughput and should be completed with a short time. Next, let's talk about some of the challenges faced by the AI storage, especially for the large language model. To achieve a better model, there needs to be a large number of tokens, parameters, and data points. From the diagram, we can see that the parameters and the data points has have been growing for many years. This will generate large data sets, checkpoints, and models. Also, the upward trend of these factors has started to slow down. The current number is still quite large. Just as the last page introduced to improve the model performance, a large number of parameters are used, and it also requires a lot of computational resources. As this picture shows, the computation consumption of the model has been rising rapidly in recent years, especially during the training process of large models. In the past few years, most AI developers have experienced the shortage of computation resources. For a technology company like OPPO, we have to purchase a lot of computing power on the public cloud. This is not only consideration for the budget, but also for elastic capability of computing power. Of course, there emerged a lot of optimized algorithm to reduce it to a certain extent, but the demand still exists. Using the computing resources on the public cloud is a good choice, but it's not an easy thing either. The computation transfer from private cloud to public cloud can be achieved, especially for Kubernetes environments. However, the storage is difficult. There are several challenges in the geographic distribution of data. That is storage cost, transfer cost, and technical difficulties. First of all, the cost of storage is rather significant. Multi-copies of data of different regions means extra cost, which will put pressure on budget, but if there is a central storage and only the whole data transfers to the different kind of the endpoints in different regions, the cost can be reduced significantly. Secondly, we need to consider the transfer cost. The first one is transfer all the data and then transfer the incremental data. However, the data transfer may not be needed by the application in different regions. The second one is just transferring the whole data. Despite this difference, there are still some common difficulties to address. One of the main difficulties is ensuring data consistency. Consistency is an important aspect that needs to be considered for multi-copies. It needs to be realized in specific data transformation system. However, when it comes to whole data synchronization, ensuring consistency is much easier and highly simplified. The data just need to be updated incrementally by the user's request, and that's all it takes. Another important factor is timeliness. Whether it is incremental synchronization or the whole data synchronization, timeliness is a critical factor in data transfer. In OPPO, to meet the training requirement for AI, we solve it by combining public cloud caching with self-built cloud storage. That is, the full data is stored in the self-built cloud, and the whole data is cached in the public cloud. Also, the latency of the first data pool is relatively increased. The performance of the repeated reads will be better. If the distance between the cloud center and the self-built cloud data center is short, that the impact can be reduced further. Next, let's talk about the model distribution. Model distribution is a big challenge for multi-regions. In OPPO, the efficient distribution of models is also built on cache system. So this requires the cache system to have several features. As the chart shows, Firstly, the system should have the ability to distribute models promptly. The cache system or CubeFS supports path configuration. When a file writes within the configured path, it can be synchronized to the endpoint of the distributing cache system, achieving a pre-warming during the write process. Secondly, there needs to be a version control system to prevent the client from accessing the stale data. Thirdly, support the pre-warming capability to enable better integration with business operations. The pre-warming is a service. The directory of the request to be pre-warmed is taken as a specific task and driven by the management system. The cache system also needs to have several technical points, capabilities. The first is high performance and high throughput, and the second is load balancing to avoid the situation where hot caches can't stand the massive requests. As shown in the diagram, after the AI training model is stored in CubeFS, it will be distributed to terminals of the inference services through the cache system. The distributed cache system is designed based on consistent hashing. The file is divided into multiple segments, and each segment is 1 megabyte in size. Each segment mapped to a slot partition in the hash ring, and many slot partitions are mapped to one cache node together. This is the routing rule. The distributed cache supports both memory and disk storage forms. In the benchmark test, each cache node within 4 terabytes capacity of ME disk can provide 50 gigabits network throughput. The bottleneck of the distributed cache lies in the bandwidth. The CubeFS distributed cache takes multiple aspects into consideration in its design. Here is some main features. Elastic cache replicas can be configured according to business requirements. There are 2 main scenarios to use multi-replicas. First, the scenario is to massive request to hold data in the regular operation of the cache system. It usually uses a single copy. Secondly, it refers to multiple regions distribution of cache. Data can be spread globally based on multi-replica form. Distance awareness means that in a scenario of multi-cache replica, cache system allows the client to select the replica cache node with the lowest network latency. Additionally, the pre-warming capability is currently under development. The requirement runs as a task which can be scheduled systematically. Large models and other business can be preheated before real operation. Finally, in order to integrate with a cloud ecosystem to adapt to more usage scenarios, a community is seeking cooperation with other communities like Fluid to provide service solutions that combines backend data persistence and the cloud data cache acceleration. In OPPO, we used to use high-performance disks to support high throughput in AI scenario, but the annual cost of storing 10 petabytes of data in NVMe is quite significant. Through data analysis of AI-driven business, it has been found that for most AI business, 80% of the data will not be read within 3 months. And typically, hot data accounts for less than 10% of the total data. How to balance computational performance and storage cost? The best way is to utilize the high performance media to alleviate the writing pressure and support the hot support reading, and migrate the code data to the lower cost storage media. That is intelligent data tiering. There are several main technical points. The first one is the life cycle system, which is fulfilled by the module LC node of CubeFS. The life cycle system is built to run Turing tasks and realize in the controllable and maintainable Turing process. As shown in the picture, the directory of the file system can be configured as the Turing path. Moreover, during the migration process, client leases are used to ensure the normal read and write operations are not affected. For data security, the original date will be retained for a certain period. After the transfer, there's a check for both sides to guarantee the data consistency. Next, let me introduce another end-user case. That is compute storage separation in CubeFS. Computing and storage have different resources requirements, so the separation of computing and storage is a very reasonable solution. Before the application of compute storage separation, CubeFS has several pain points in storage as introduced in the chart. First, the storage capacity of single node is limited. The inspector should pay attention to disk space and finish the operation timely. Second, the SRE has to use high capacity disk for each node to ensure the system runs smoothly. The cost is significant. Third, on the other hand, similar to situation with capacity, the disk performance can't fully utilized because it can only be accessed by specific partitions. Fourth, once the space is balanced between partitions or nodes, the data migration and balancing will be quite complex and may affect online services. All the factors contribute to poor stability and the factors related to storage. So it's better to leave the professional things to professional teams. This is the first edition of architecture. To maintain CubeFS original structure, the storage layer uses a single replica model of CubeFS to make sure that the volume distribution are separate from each other. CubeFS uses two CubeFS clusters to store different replicas. This approach offers nearly unlimited storage space and enables data layering, significantly cutting cost. At the same time, it adjusts to CubeFS original architecture well. However, it has drawbacks. Because we use two different single replica volumes in CubeFS storage, the consistency can't be guaranteed by the storage because the two volumes can't sense each other. The storage platform doesn't know the relationships of the two volumes. The check module needs to do the inspection periodically to guarantee the consistency. Once there's a bad disk of CubeFS because of a single replica and can't be repaired automatically. The repair depends on the checker module of CubeFS. At the same time, to enhance the repair speed, the bad disk should be detected promptly by CubeFS. What's more, the inspections, data traversal, and repair needs a long time. The drawback of this system architecture influences the online services to a certain degree, causing delays in processing requests. Finally, the CubeFS team updates the whole architecture and uses CubeFS as a shared storage. CubeFS doesn't need to care about data repairs. Compared to the design on the last page, the reliability and stability are much better than those of design with only one replica. And since the storage fully depends on CubeFS, the promote repair disk failures can be achieved. Moreover, the operation and maintenance are simple. CubeFS can restore data on its own with SR intervention, leaving business unaware. The last end-user case is compute storage separation with SDK. The compute and storage separation in ClayHouse is based on the Fuse client, and the storage is accessed by the mount point. The Fuse is a standard tool to access storage. However, in reality, Fuse can affect the whole performance. As shown in the slide, the SDK has the following features. SDK has high throughput, performance, and stability. This is because SDK totally run in the user mode and bypass the kernel mode. At the same time, it avoids many constraints of Fuse itself, such as the boot block size. Moreover, it can also adapt to some special requirements in the user mode. What is shown in the figure is a typical computing service based on LSM tree. This service stores both the workloads and SST files in CubeFS. It's a typical append-only write application for storage. This is a firmware architecture of key-value storage, and it's usually used for online services for massive key-value storage, such as Redis and RosDB. The requirement of the stability of data storage is extremely high, especially for a P99 requirement should be kept within 1 millisecond. Based on the requirements, we also have actually made a lot of optimization on the background. I won't introduce it in detail here. Last year, the community released several versions, including 4 official versions and 3 beta versions. This year, CubeFS already released the data tiering version. And also, we will officially release another 3 versions. The first one is release 3.5.1, which mainly focuses on distributed cache, and is mentioned a lot in today's speech. But this is not the final version. There will be an enhanced version released 3.5.2 as the second phase of the distributed cache. At the same time, the version will be a stability enhanced version, including features such as metadata automatic migration. As mentioned in the speech, we will put the manuals memory into RosDB storage to reduce the memory costs, which is also a basis for hybrid cloud data tiering. If we still have the energy, there are some aspects that we want to schedule to do. The first aspect is the performance improvement. And the second aspect is hybrid cloud, where we want to build a complete hybrid cloud system, support the S3 offset storage, and to make the data flow freely. Thank you all for listening patiently. If you have any questions, you're welcome to raise them. Or contact us through the Slack. I will do my best to answer. And at the same time, I hope you can pay attention to CubeFS and its community development. Okay, thank you. Thank you all.